With this lecture comes a warning. There is a handout posted on Limits at Infinity Part 1, and that handout has sample problems, which means worked out problems. And so on the exams, quizzes, you're going to have to do what the sample problems do there. So look at it, because this is what will be required of you. A little essay of speculation will get you 1 point out of 10. What will the parabola do as we leave the picture, the part of the graph that was actually drawn? What if we would take a long walk on the x-axis? What would happen? And in this case, it's very easy to see that you take a large number and you square it, you're going to get a large positive number. The larger x gets, this thing gets even larger. In other words, if we graph this thing using a graphing calculator, we would see this. This is kind of describing the tendency of the function. Suppose we're looking at the graphing calculator, looking at this thing on the graphing calculator, and let's say in the middle there is the parabola x squared, y equals x squared. What does this mean? The graph leaves the depicted part in the right and up. Now we're going to have to be a little bit more specific like that, and we should develop notation for this. So how can we describe with algebra what is happening here? That there is a point for every x, but the larger x gets, the farther it is, and just keeps increasing. Furthermore, it just outgrows any number you can think of. So we should have notation for this. Here it is. All right, there is a lot to digest here. LIM is for limit. It's going to be a whole new thing. Well, for one, it will very quickly join the items on the complete analysis of a function. Now this here tells you the expression. In this case, y equals x squared. Down here, these are instructions. This is an instruction. Oh, we read it, x approaches infinity. And that is short for it outgrows any possible number. So think million, it will outgrow it. Think gazillion, it will outgrow it. And also, it is not a fixed gigantic number, but keeps getting larger and larger in the positive. So we have these instructions to think of x as gigantic, positive, and constantly growing, jumping over any bound we can think of. Visually, would be that we take a long walk on the positive part of the x-axis. And this is what the y coordinate is doing, right? So as x approaches infinity, the graph of x squared approaches infinity. Now how would we rewrite this tendency? What would be the algebraic translation of this? If we go to the left and keep going and going, what's going to happen to the y coordinates on the graph of y equals x squared? So we're going to say limit of x squared, but now as x approaches negative infinity, this is an instruction to think of x as a gigantic negative number, but not a fixed one. It's one that keeps growing. And what would be the answer? The answer would be it's still infinity, right? How could we express these two things? This one would be, we would say that the limit of f of x as x approaches infinity. So now we have to imagine to walk on the x-axis. The numbers are gigantic, and what does f of x do here? Where do we have to look for the graph? And the answer is way below, right? So here is negative infinity. Now this one, on the other hand, now x is going to be negative and y is going to be positive, right? This is going to translate to limit as x approaches negative infinity of f of x equals positive infinity. This says on the left and this says way up. So the graph is entering the graphing calculator screen from here and enters right bottom. So we have these tendencies that we're just developing a new language to express. Okay, let's see another example. I actually want to write this down because this is important. So we read this as x approaches infinity. So x approaches infinity means not only that x is a large positive number, well, almost a number, except for it keeps changing the value. It just keeps growing. It's not a fixed number. So more like x is a variable taking larger and larger positive number values. X approaches negative infinity is the same thing, but now we're instructed to think of x as a constantly decreasing negative number that gets below any bound we can think of. So x is large, x is negative, and it keeps growing, and it outgrows any number we can think of. Why do I keep bothering you with this bound thing? Why don't I just say increasing? Here is the problem. You can increase and not approach infinity. For example, if you take 1 over x and you flip it upside down, as we approach to the right, this function, this graph is increasing, but yet we don't feel like it's approaching infinity. As a matter of fact, this will approach 0, right? So it's not enough to say increasing. We somehow make it, well, I'm just going to keep going back to outgrow any bound. So it becomes larger than any fixed number. So here we can say that the limit as x approaches infinity of minus 1 over x is 0. Now that's a much more interesting limit. And in this particular case, it means that we have the same instruction about the where, which is the horizontal. X approaches plus infinity. And the limit being 0 means that as we take those larger and larger values for x, the closer and closer we get to 0. Well, the problem is that we're also getting closer to plus 3, right? So there is something special about 0, sort of the thing that gets really, really, really close to, and annoyingly, we're not going to define limits. So there's going to be a lot of waving of arms and appealing to your intuition, and then we suddenly will draw a line and be all rigorous. It's almost like we're taking 2 courses. So, and this is the vague part. This is the one where we're not defining. But the fact that this graph approaches 0 as x approaches infinity means the following. The farther we go to the right on the x-axis, the closer the y numbers are to 0. And if we have a limit, then the y-coordinate of the graph will get arbitrarily close to 0 eventually. By the way, visually we call it a horizontal asymptote, right? All right, so a horizontal asymptote is really a right-hand behavior. The limits of functions at plus infinity and at negative infinity are sort of the edges of the picture. It's called the end behavior. So end behavior of the functions is the next item on our list of complete analysis of a function, where you have to state the left hand and the right hand. And the limit needs not to exist at all. There is going to be lots of times when the limit doesn't exist. So a horizontal asymptote means that the limit as x approaches infinity of f of x is a constant number, c, in this case 0. That's what a horizontal asymptote. But in this particular case, what happens is that we get closer and closer and closer and closer, but we never quite get there. That's sort of a romantic notion of getting ever closer and closer, yet never getting there. There are plenty of functions that cross the limit plenty of times. So this is just one specific example for limits. They are not all this romantic, so to speak. So the end behavior, well, it's part of the graph, right? You have seen there is always going to be graphical, visual, and algebraic. So you have seen, I guess in case of 1 over x, we would draw something like this. So this is what we would depict on our picture, on our graph, which, as I said, is a summary of all these items. But to express this algebraically, we're gonna be asked to find limit of f of x as x approaches negative infinity, which is the left hand behavior. So what is the function doing when x is a gigantic negative number and keeps getting larger and larger negative? And the limit as x approaches infinity of f of x is the right hand side, the right end of the picture. So these are our new concepts. Well, there is still plenty to unpack here. We're going to start with end behavior, and we're breaking it up into 2 parts. The first part is basically you have to understand and present the end behavior of basic functions. For example, like log 2 of x looks like this. Now, let's discuss the end behavior. What can we say about the limit of f of x, or log 2 of x, as x approaches infinity? In other words, what is the function doing at the right edge of the graph? And the answer is not exactly obvious, because it looks like, yes, it's increasing, but it increases sort of slow, at a slower and slower pace, and it may be possible that it starts to level out like that negative 1 over x did. So this is where we need to differentiate between increasing and outgrows any bound. So what we need to ask ourselves is, okay, it's increasing, but does it approach infinity? Does it grow beyond any number we could imagine? And so let us ask ourselves, does this graph ever reach y equals 10? Well, yeah, log 2 of 2 to the 10th power would do the trick. Would it go to 100, 1,000, a million? And it's basically, yeah, we would have to be really, really patient, but the y value of x equals 2 to the 1,000th power, which is humongous, is 1,000. So yeah, it goes slower and slower, but it's still marching towards infinity, which is to say it grows beyond any positive number we can think of, beyond any negative number too. And you kind of have to store this. This is a basic function. Oh, here comes the fun. What about the other end? Well, what is the function doing when we take a book at the left edge of the paper, thinking of the x values as larger and larger negative numbers? Well, they're nowhere to be found. The domain of log 2 of x is all the positive numbers, right? And so no function, no limit. I accept a lot of answers here. I accept the bureaucratically sounding not applicable. I also welcome nope. Undefined would be the official answer. So the left end behavior is undefined. No function, no limit. Well, let's look at the other example. This one is interesting too. So on the right hand side, the bigger x, the really much bigger the y is, so it's really easy to see that the right end behavior is infinity. The left end behavior, on the other hand, is finite, very finite. That's a zero limit. So that's kind of interesting. What about square root of x? The left end behavior is that the left limit is undefined. Limit as x approaches negative infinity of square root of x is undefined. No graph, no limit. On the other side, we have again the same issue. Okay, it's increasing but slower and slower. So does it level off or keeps marching towards infinity? And the question to ask: does y get beyond 1,000, 10,000, a million? And it will in this case, because if you want 10, you just have to wait until x is 10 squared, right? For a million, x being a million squared will do the trick. So the y coordinate, even though slower and slower, it does outgrow any number we can think of. So in other words, the right-hand side limit is infinite. There are lots of ways of not having a limit. It doesn't have to be because there is no function. There are all kinds of other ways failing to have a limit. So having a limit is sort of an elite club. Not all the functions do it. Consider our good old friend sin x. First of all, when I ask, what do you think the limit is at infinity and negative infinity, I'm not asking you to figure out something using logic. This is a matter of definition. Furthermore, we're not going to formulate a rigorous definition. So these things could have gone very differently. But in this particular case, as x approaches infinity, what is the graph doing? So if x is a crazy, really, really large number and growing further, what is sin x doing? What is the y coordinate of this graph doing? And it's kind of boring. It just oscillates back and forth with the same speed. And it doesn't really it doesn't approach infinity or negative infinity. It just stays within -1 and 1, but it is not getting close to anything, pretty much. This is undefined as well. It has to either go really, really large and stay there, we'll discuss this, or really, really, really close to a number. And neither of those is happening here. Same with the negative infinity, right? Let's look at tangent x. If this is rusty for you, work on these. Now, what tangent x is doing is that it has, say this is pi over 2. So just on this interval, it basically goes from negative infinity to positive infinity. But then it does it again and again and again. So what gives? We could have defined the end behavior to be infinity, but we rather went with undefined because we want the graph to get large and stay there. Now what do we mean by staying there? So this is undefined too. So the limit as x approaches infinity of tangent x is also undefined. Let me show you two examples. See the difference? There is some hesitation that is going up and going down, but on the long run, this one trending upward. This one has a limit and it is infinity. So here, limit. We mathematicians decided to go with undefined here because we want the graph to, we want the function to outgrow any number eventually, and outgrow means it gets above and stays there. In other words, there should be a point from which I could draw a straight line and the entire function starting from here is above it. See, there are these lines. Okay, the rest of the function is above it. That will never happen here. It just keeps coming back to zero. So it has to get arbitrarily large and it has to kind of stay that arbitrarily large. So this one is undefined. So this is why tangent fails to have a limit, because it just keeps coming back. And while we're on trigonometry, I'm not going to go over it because it takes a lot of time, but you should know the story of how we defined arctangent or inverse tangent of x, because inverse tangent of x is really, really famous. So if you recall, tangent had all these threads, these vertical threads, and to generate the inverse, if we want it to be a function, we have to just pick one thread. We have to restrict the function so it is one-to-one. And so first we restrict the function into the interval between negative pi over 2 and pi over 2. And then on every point on this graph, we simply swap the x and the y coordinates. So whatever was x becomes y, whatever was y becomes x. What we're going to get is that vertical asymptote at the vertical asymptote with equation x equals pi over 2 will become a horizontal asymptote with equation y equals pi over 2. And so when we swap all the coordinates in every point of the graph of tangent, we get the inverse tangent or arctangent, and then there is a limit. These are the two notations for arctangent of x. So at plus infinity, the limit is pi over 2. And at negative infinity, that limit is negative pi over 2. So we have seen a few examples. So as I told you, there are going to be two parts to end behavior. One is just the basic end behavior. I'm not going to cover all of them. That would be boring for you to watch. And I think I have shown you enough examples. Let's look at the algebra. So monomials. Poly in Greek means many. Polynomials, the poly in there means many, and mono means one. So monomials are polynomials with length of 1. So we're going to first look at end behavior of monomials. Let us first acknowledge that with the exception of just a number, if it has at least one x in it, then monomials end behaviors are large, infinity or negative infinity. It's just which one. And so really there are just 4 possibilities. This is what I call the 80s dance. There is no other option. If we just acknowledge that it's infinity or negative infinity, all we have to worry about is what is the sign. So let's see if the monomial is something like minus 2x to the 6th power. I never know how to approach them, in what order, because this is left to right, but this is easy to difficult. So this time let's start with the really easy one. Negative 2x to the 6th power is really short for negative 2 times x times x times x times x times, how many? One more. Times x. And x is gigantic, outrageously large, right? So is this number a huge positive number or a huge negative number? And the answer is, well, if x is all positive, then there is just one minus sign, making the whole product negative. Now the other side is a little bit trickier, because now for the limit as x approaches negative infinity, we are instructed to think of x as a gigantic, outrageously large negative number, right? So how many minus signs do we have? We can say that, well, x to the 6 is alone is definitely positive, and then we multiply it by negative 2, so it is negative. We can also say that Well, I see 7 negative signs. That's negative. Either way, just get there. So this is like, take x squared, which looks like this, right, and flip it upside down. This function has descent behavior, right? Comes in below, leaves below. There isn't much variety here. The question is the degree odd or even? Is the leading coefficient positive or negative? That's pretty much it. So let's look at f of x equals 1/2 x to the 7th power. So let's start with the easy one. If x is a gigantic positive number, there is no negative sign inside. This is just going to be positive as they come, right? So the limit there is plus infinity. Now when x is negative gigantic, then how many negative signs are there? In the product 1/2 times x to the 7th power, and the answer is 7. That's an odd number, so that means we're dealing with negative infinity. In other words, we're dealing with this guy here, right? Comes in at negative infinity and leaves at plus infinity. If we would multiply this guy, by -1, we would flip it upside down. Basically, think of even degree like x squared. And then this makes sense. And then flip it upside down. This is what even degree monomials do. And then the odd ones are like kind of finicky. They never come in where they live. And it's just think x or x cubed. So you know this is going to be the one with positive leading coefficient. Flip it upside down. That's the same thing with negative leading coefficient. I think there is no point in going through all 4 variations. I think you got the idea. So monomials. Then there are radicals, even, odd, logarithms, exponentials. We covered the whole lot. And look at the trig functions too. I know we didn't start reviewing trig, but there's going to be a big bite anyway. So these are going to be basic limits, and they are intuitive, and you just have to know and understand the basic functions. But then we're going to start sort of trying to perform operations on limits, which when they are numbers, they absolutely behave like numbers. So in other words, f of x equals 5 and limit infinity g of x is -2. So what does this mean? Both of these functions have a horizontal asymptote, at least at the right? As x approaches infinity, y approaches 5. As x approaches infinity, g approaches -2. The farther we go towards infinity, the closer they are to these fixed numbers. So what do you think we will get if we take a new function, f plus g of x, which is defined as, well, compute f of x, compute g of x, and then add. So we say pointwise. So f plus g of x is what you think it should be. But this plus here is between 2 functions. This is between 2 numbers. So what do we think? So the question is, given this definition, is what happens if we add the number really, really close to 5 and a number outrageously close to -2? And if your intuition is telling you that we are going to be outrageously close to 3, you are right. So this limit is 3. If we divide a number really close to 5 by a number outrageously close to -2, the quotient will be very, very, very close to -5/2. So we can apply sort of the regular operations on when you have just numbers, except don't divide by 0. Let's leave it for another day, or let's think about it. What happens if you take a function that has a limit and it is 0, and then you put that into the denominator? What's going to happen to that limit? You think about that. So for now, let me just show you that we can also work as if they were numbers if just one of them a number. For example, what happens when we add a number really, really close to 12 and a gigantic, outrageously large negative number? Well, we're still dealing with a very, very large negative number, right? That 12 is just really insignificant compared to not just the size, but it keeps growing too, right? What about limit as x approaches infinity of f of x times g of x, which is how we define the product of 2 functions? Well, it's going to be -infinity. How about f of x minus g of x? So what happens when we start with a number really close to 12 and we subtract a gigantic negative number from it? Well, to subtract is to add the opposite, so we are now up to plus. So, in other words, we can We can think of limits just as we think of numbers, as long they are both numbers, or at least one is a number. However, all bets are off when you have two limits that are infinite. Now, what's the deal with this one and what's the deal with this? So the first one says take an outrageously large positive number and another one and add. So it is very clear, sort of infinity plus infinity is infinity, but infinity is not a number and operations on it are a little bit tricky. What about here? Now we take a gigantic positive number and subtract it from another gigantic number. Well, who is bigger, right? This is what we call an indeterminate. Think of indeterminates as gigantic opposing forces. F of x wants the answer to be plus infinity, minus g of x wants the answer to be negative infinity, and we don't know which one wins out. As a matter of fact, we can make up examples with all kinds of different outcomes. We can make f of x much stronger, or g of x much stronger, or the same. So in other words, when you see gigantical opposing forces, you're not allowed to use the usual intuition because it breaks down anyway. So indeterminates are sort of infinity minus infinity, or infinity over infinity, infinity over infinity. Let me show you three examples. We can take x to the 7th divided by x squared. The top is going to infinity, the bottom is going to infinity. Let's agree that we are talking about at the right edge. So as x approaches to infinity, both these approach infinity. But we know what it's doing at infinity because we can simplify it. We can simply consolidate this expression into x to the 5, and so that approach is infinity. Well, what about x squared over x to the 7? That too is infinity over infinity, right? And now we have 1 over x to the 5, which approaches, what does 1 over x to the 5 approach? So limit as x approaches infinity of 1 over x to the 5. So let's see. X is gigantic, positive, and growing. Now we raise it to the 5th power. Now it's even bigger. And now we're putting that into the denominator. What does that do? And it is very much like what 1 over x does. The end behavior of 1 over x. This one approaches 0. And then we can have 40x cubed over 10x cubed. Both approach infinity, but the x not only consolidated, that cancels out. This is a constant function, and constant functions are as close as it gets. They always have limits, and that constant value is there. So infinity over infinity is something we're not allowed to further speculate, because it depends who is more infinite than the other, right? The first part is basic functions, which by now pretty much finished, and then we're going to look at indeterminates, how to deal with indeterminates. And basically, in case of indeterminates, we will have to do the following. We have to stop speculating and massage the expression until we bring it to a form that is not an indeterminate. And then we use our intuition to evaluate the limit. And it's on a case-by-case basis. It's going to be a little bit of a cookbook. If the indeterminate does this, then this is what we're going to do. I just want to show you a few indeterminates that are really very easy to resolve. I really like this one. So if x is gigantic, 2 to the x and 2 to the x plus 5 are both humongous, right? So we're talking about an infinity minus infinity type of an indeterminate. So because this is what we see, we are absolutely not allowed to conclude from here. We have to do algebra to bring it to a form which is no longer an indeterminate. That's mandatory. But this is really easy because, you know, a to the n times a to the m is a to the n plus m. And therefore 2 to the x plus 5 is 2 to the x times 2 to the 5, right? We're applying the rule kind of backwards, which is 32 many 2 to the x. So we have 32 many 2 to the x, from which we subtract just one of them. And that is clearly not an indeterminate, right? We could have sort of waved our arms and say that this is bigger, but the thing with speculating on indeterminates, out of 100 times, 99 times the intuition will work, and then the 100th case is just going to be a mess. And that's why we need rigorous approach with limits. So this limit here is infinity. Yeah, just think about it. If we add 5 in the exponent, that means we are throwing 5 additional factors of 2 at the product 2 to the x. So that's multiplication by 32. Okay, so I thought this is cute. What else is on this handout? So these are easily resolvable indeterminates. There is another one. So both of these functions approach infinity, so we are again dealing with an infinity over infinity type of an indeterminate. But this expression can be easily consolidated, because if you have a common base and you subtract two logarithms, that can be simplified into log 2 of their quotient. It's a very fundamental rule in logarithms. Yeah, this is the week when you should work on the logarithms. So what do we have? We have log 2 of 24x over 3x. X cancels out, and we have log 2 of 8, which is the limit of the constant function 3, which is 3. So that we may not have seen if we're just speculating right there. Okay. There is another type, you're going to love it. There are two types of exponential function. For an exponential function, the base has to be positive. But then the question is, okay, it's positive, but is it greater than 1 or less than 1? So if the base is greater than 1, we have exponential growth. Like think 2 to the x, but even 1.01 to the x will do this. And if the base is less than 1, we have exponential decay. It's literally flipping this thing about the y-axis. So f of x equals a to the x when a is less than 1, still positive. So that's exponential decay. So when you have something like this, so we have these scary looking exponential expressions both going to infinity. And so this is an infinity over infinity type of an indeterminate. It's a very simple one though, because we're going to be able to consolidate these two expressions into a single exponential expression with x in the exponent. And then we're going to have to ask ourselves two questions. Okay, is the base bigger than 1? Because then we're looking at this graph, or is the base less than 1? Because then we're looking at this graph. And the other question is which end, the left or the right? Let's work this out. Here is what we're going to do. The goal is to peel off anything else, just leave x in the exponent, because we want to use this rule of x. Using rules of exponents, 3 to the 2x minus 3 is the same as 3 to the 2x divided by 3 to the 3, right? We usually use it this way, but it's true back and forth. And 3 squared, 3 to the 2x is the same, here is the rule, we're going to use this 8. So it's going to be 3 squared to the x over 27, and that's 9 to the x over 27. Very soon you're not going to need to write anything. You're going to be able to peel off this extra fluff mentally without writing. So we're talking 9 to the x times 1 over 27 times 5 divided by, now this comes off as 8 to the x times 8 squared, right? So this is the drum roll part. We're basically looking at 9 over 8 to the x power. So which picture are we looking at? This one or this one? 9 over 8 is greater than 1. Therefore, we're looking at this picture. And because we're looking at x approaches plus infinity, that means we're looking at the right side of this. And so the answer is plus infinity. But this one is gigantic, so the whole thing is going to infinity. Something that is a quotient, but very easy to divide through. For example, so this is our last example. Limit as x approaches 3x minus 1 divided by x. And the top is, as x approaches infinity, the top is approaching infinity, and the bottom is approaching infinity. So we are not allowed to speculate any on this. We have to massage this until it is no longer an indeterminate. And it will get us there if we just divide through. 3x over x is 3, and now this is no longer, let's see if this is still an indeterminate. Is it? X is gigantic, put it in the denominator, now it's tiny, really, really, really small, almost 0, and we're subtracting that from 3, so the limit is going to be 3. Now if we go back here and say, okay, imagine a number so outrageously large. It has more zeros than the largest number I can think of. Who cares about this subtraction 1? That one is so insignificant there. It's almost like it's not even there. If we are just a little bit sloppy and we pretend it's not here, then 3x over x is 3. So that's how you can get the answer in an intuitive way, but this is how you have to prove it. So someone at some point defined rigorously what limits are. So what you're looking at is a list of properties that were rigorously proved based on the definition. These are also very intuitive, especially considering that this sheet does not include the most interesting cases when L or M, any of the two limits, is infinitive. If you look at the conditions L and M and C are real numbers. So we don't have any infinity or negative infinity here in the mix. Those we are not allowed to use. This is only for finite numbers. If the limits are both numbers, then the sum rule is that the limit of the sum is the same as the sum of the limits. So it doesn't matter. Take one limit, take the other, add, or add first and then take the limit. Same thing. Now for number 5 and 6, this is the beginning of something that we're going to keep doing, so might as well get used to it now. For the purposes of calculus, a product of two functions is a much more complicated animal than just a function times 2, or a function times a fixed real number. So we will have different names for them. The product will refer to functions that you multiply, and the constant multiple rule means we just have a function that we are multiplying by a constant. This is going to be a recurring theme of distinguishing in our language between those two cases. Turns out that constant multiples have all kinds of nice properties, and products are kind of mean. And understand it, this is basically the stuff that we're going to assume. We're not going to prove it. First was the definition, then these properties were rigorously proven by someone else. Now we have these properties, and from now on we're going to prove everything else rigorously. So that is the plan. Any questions? Any questions? Okay. Thank you for watching.